Okay, it's time that we look at something from 2.3. So in 2.3, we have a certain type of problem, a mixture problem, that we'll use differential equations to explain. And here's this scenario. There's a tank and it has a certain kind of solution, such as water and salt. And it starts at a certain concentration, okay? So the way that this problem begins is, let's suppose that there's a 100 liters tank. It will always have that volume. It will always have 100 liters in it. But it begins at 2 kilograms of salt in the tank. So 100 liters volume of, say, water, 2 kilograms of salt inside it. And here's what happens. We let a different solution, a different concentration, flow in, and we suppose that we have perfect mixing in there, and then whatever flows in also exits. Okay, so you put one kind of solution in at 5 liters per minute at a certain concentration, half a kilogram per liter. It's mixed perfectly, and it flows out at the same rate. That keeps the volume on the inside constant. Okay. So that's what happens, and we're after this function that tells you the mass of salt in the tank at any moment in time. All right, so when we're looking for the function a of t, it is the number of kilograms of salt in the tank at time t. T's in minutes. All right, now let's analyze some things about the function. That's what I'm calling the function. That's what I'm calling a of t. All right. Now, so initial condition. If we read the question, and I posted this question, it's now on Blackboard with the lessons. It's my own question that I made up. I've explained to you what happened so far, but it does say that in this tank is initially at time t is equal to 0, 100 liters of water and 2 kilograms of salt. So there's your initial condition. If that's what a of t is, then a of 0 has got to be 2 kilograms. That's how you start out. And also I ask on my document I posted, what's the limit as t goes to infinity? Well, here's what I would expect to happen. We'll see if we're right when we solve it, but if this is what goes in, and let's say it just happens forever and t can go to infinity, what shows up in here in the long run is going to be more like the solution that's flowing in. Okay, so if this is what goes in there forever, then eventually you'll have 100 liters at this concentration. All right, so say you have 100 liters and there's half a kilogram of salt per liter. Well, that's going to be 50 kilograms eventually. Okay, so that's what I would expect the long-term limit to be. If a of t is just what I say here, something that tells you how many kilograms of salt are in the tank at any time. And this has got to be the limit as t goes to infinity. All right, now where do differential equations come in? We have, here's the principle that explains what happens in the mixing tank. All right, this is how we get something about the function a of t in the form of a differential equation. The law that governs what happens in the tank is the rate of increase in that function. What's another word for that? The derivative, dA dt, which would be measured in kilograms per minute. Okay, so that is equal to the rate that salt enters the tank minus the rate that salt exits the tank, because it's going in and it's going out, because there's some kind of salt solution in there at all times, drains out, and then some other kind of salt solution goes in. So if you can just say what all this stuff is, then you get your differential equation. All right. Okay, well, let's see if we can do that. Now notice about the units. If we can say that, well, the rate of change in the function a of t is going to be dA over dt, that's kilograms per minute, the units of whatever this is can't be any different. And I have two terms subtracted. They both have to be kilograms per minute. So if you're trying to figure out what these are, knowing the units is probably a good clue to get you started. Okay, so this differential equation is, well, that I don't know that because I don't know this function, but this rate of change would go by dA dt, A being the dependent variable, the amount in kilograms, T being the independent, time in minutes. Okay, so how fast is, in kilograms per minute, is salt entering the tank? Well, look, you could just take these units the way they are, 5 liters per minute at half a kilogram per liter. What if you multiply those? What are the units going to be? Kilograms per minute. Okay, so that's just going to be 2.5. Actually, what's going in that tank is 2.5 kilograms of salt per minute, and that's what you wanted. Okay, about the rate that salt exits the tank. Well, so what's happening? Exiting the tank are, well, I guess we'd have to put it like this. Here's what happens. What's in here at any moment? Well, I guess we'd have to say at any moment there's A of T kilograms of salt in the tank. At any moment in time, that's what's there. All right. Let's do like this, in fact. There's A of T kilograms of salt. Okay, we're making our salt water. And there's 100 liters. That's always true. Okay, that's how much salt is in there in terms of the absolute amount. And this is the volume of the total solution. Okay, and it's exiting, like whatever is in there mixed all together at any moment is exiting at the rate of 5 liters per minute. Okay, and so look at that. That would give us what we want. I mean, I took what I know to be in there, and I know how it's exiting. Whatever is in there is going out like this, and I get kilograms of salt per minute. That's what I wanted. That's what the unit that I wanted for the rate of exit, the rate that salt exits the tank. Okay, so that's going to do it. And if we multiply, we get the function A of T times 5 over 100. And the way that I'll write that is I'll say minus, I get coefficient 0.05, and then times that function A of T that I want. I'll just call it A. That would be typical in differential equations. We say y, if y is the dependent variable. We don't say f of x or y of t or whatever it is. A is going to be this thing. Like I said, the dependent variable. Well, so a differential equation involves an unknown function and its derivative. That's what differential equations are. And now I have a differential equation. Okay, now say we get there. We've got our differential equation. That's good, but the next thing to think about, I guess with any kind of equation that you get, is how do you solve it? Different equations are solved different ways, and you have to figure out what kind this is. And that is a separable differential equation. Okay? And we've learned elsewhere how to solve those. Separating the variables, I'm going to get this. So I get the, by mere separation, the dependent variable A on the left, and then over here, I guess I would get 1 times dt. So that's separation. All right, that's what we get. Now, let's say that you integrate both sides, and this would be a basic U substitution logarithmic form of integration. And we'll get coefficient negative 20, natural log, absolute value, 2.5 minus 0.05a. A being this function that tells you how many kilograms of salt are in the tank. Okay, now that's on the left. That's what we get by U substitution. And over here, T plus C. All right, that's like many other separable differential equations that we get. All right, now let's see. Let's say that we've seen this. We can do that kind of thing because we've seen it already. I'll give you what the solution will be if we solve for a, as it is that we desire to know this function a of t. So if I do that, if I go through the usual procedure, I'll get a of t is, now I get this constant coefficient, we'll call it k. E power would be negative t over 20. Okay, and then plus 50 is how it's going to work out. All right, so there it is. And what would we call that? We would call that the general solution. And what's that mean? Well, if this is the way salt goes in and goes out, then the function a of t has this general form. Now, if I know how much salt you start with, that's an initial condition. And I do know that, and that would turn a general solution into a particular solution. So if let's do this now. To find the particular, which is our ultimate goal, I happen to know that a of 0 is 2. Because it did say, as I mentioned, that we start with 2 kilograms of salt in the tank. And so say that that's going to be 2. That's going to be k plus 50. Then k has got to be negative 48. Okay, so now I know the constant, and that would give us our particular solution. Okay, so let's do that. I'm going to go ahead and put that over here, and I'm going to update this. So a of t is negative 48 times e to the minus t over 20 plus 50. All right, and let's cross this out and say, well, that's now our particular solution. It's particular to the case that salt goes in and out like so, and we have this initial condition to start things off. Okay, so I get my particular solution. That's the objective. One more thing, without even knowing anything about differential equations, I thought that the limit as t went to infinity for that function would have to be 50. Just because although this goes in and this goes out and it's all mixed together, as that happens over time, what's in here is just going to resemble this. Okay? All right, and is that true? Should the limit as t goes to infinity be 50? Well, what happens there if t goes to infinity? This exponential term goes to 0 ultimately, and I suppose our limit is just going to be 50 kilograms. Like we said, that it ought to be up here. Okay.